Hello, my name is Kenny Aliben, and I'm the session chair of this session at Eurographics. And it's my great honor and pleasure to present the papers of the Simulation of Soft Materials session. I would like to introduce the first paper. It's entitled Soft SMPL, Data-Driven Modeling of Nonlinear Soft Tissue Dynamics for Paramedic Humans. And it's written by Igor Santisteban, Elena Karkas, Miguel Ottodui, and Dan Casas. And Igor will do the presentation. Please go ahead.
Hi, my name is Igor and I'm going to present you SoftSimple, data-driven modeling of nonlinear soft tissue dynamics for parametric humans. This project is motivated by the importance of soft tissue dynamics in the creation of compelling human animations. For example, the following video shows a comparison between the standard simple model, which lacks soft tissue dynamics, and our method. The soft tissue deformation cited by SoftSimple result in a more realistic animation, which otherwise appears very rigid. Our model is trained on real-world data and can reproduce very rich dynamic effects while running at interactive frame rates. Most existing methods use physics-based models to generate soft tissue dynamics. These models have many advantages, such as supporting interaction with external objects and generalizing well to new motions. One example of a physics-based model is the one developed by Romero et al., which is also being presented at Eurographics. So, if you are interested in the topic, I recommend you check it out. Unfortunately, due to the inner complexity of the human body, physics-based models tend to be slow and are not suitable for interactive applications. In contrast, data-driven approaches learn soft tissue deformation directly from data, avoiding the physical simulation instead. Existing data-driven methods lack interaction with external objects and generalize poorly to new motions and shapes. Despite these limitations though, data-driven methods have become quite popular because in comparison with physics-based approaches, they are very fast. Our work focuses on overcoming the generalization issues while keeping the computational cost low. So, why is it hard to train models that generalize well? We identify three main challenges. First, soft tissue deformations are highly nonlinear and vary greatly depending on the body shape. Second, due to the complexity of acquiring ground-truth data, existing datasets are quite limited. In this work, we use the dataset of Dyna, which contains sequences of 3D scans of 5 subjects captured at 60 frames per second. Unfortunately, due to the small amount of body shapes, training on such data leads to overfitting issues. The key insight of our work is identifying the source of this overfitting, which is what we call entanglement between motion and shape. This one requires some explanation, but it's a key point to understand the contributions of our work. To explain the entanglement problem, let's first take a look at the bigger picture, what we are trying to achieve. Roughly speaking, we want to train a regression model that, given some motion descriptor gamma and some shape descriptor beta, predicts the soft tissue displacements delta. For now, we can think of this input descriptor just as a bunch of numbers that encode motion and shape information. Intuitively, we will expect the shape descriptor to control the magnitude of the displacement. That is, if the body has a lot of soft tissue, the displacement will be bigger than in the case of a lean body. In an ideal dataset, each subject will have a different shape descriptor, but the motion will be exactly the same for all of them. This way, during training the model will see that the same motion descriptor alongside different shapes produces different soft tissue displacement. Since the shape descriptor is the only input that changes, the model will easily identify the effect that this parameter has on the soft tissue, and it will generalize well to new body shapes. Here comes the problem. The data we use comes from 3D scans of real people, and people tend to move in their own fashion. As this video shows, although they are all performing the same exercise, the resulting motion is not the same. Notice how each person runs at a different speed. Some of them move the arms a lot, while others don't move them much, and so on. Basically, there are many differences that are unique to each subject, and that introduces the following issue. In our ideal dataset, each subject could only be identified by this shape descriptor, but in the dataset we got, there are features in the motion that are also unique to each person. Nothing prevents the regressor from ignoring the shape descriptor and using these subject-specific features to control the magnitude of the soft tissue displacement. It will still predict the training data correctly, but we'll end up with a model that is useless because it won't generalize to new body shapes. This is precisely what we refer to as the entanglement problem, that is, the presence of features in the motion that are highly correlated with the body shape. The good news is that there are at least two ways of solving this problem. Since it's basically an overfitting issue, we could just gather more data, but obtaining 3D scans of soft tissue deformations is a difficult and costly task. So we propose an alternative approach. We are going to disentangle motion and shape by removing all those features that are particular to each subject. To do so, it is useful to make a distinction between two types of entanglement. Static entanglement refers to subject-specific features present in individual poses. Some examples that we've observed are the rotation of the hands, the aperture of the armpits, and even the inclination of the neck, which are unique to each training subject and quite consistent across frames. Meanwhile, dynamic entanglement is related to the way each subject performs a motion, like the speed, the style, or the range of motion of the limbs. The main contribution of our work is identifying these two sources of entanglement and proposing ways to address each one. For static disentanglement, we introduce a novel pose descriptor that normalizes poses across subjects. Meanwhile, we avoid dynamic entanglement by augmenting the dataset using motion transfer. Additionally, we complement these contributions with a nonlinear network architecture that has two main components: an autoencoder that produces a compact subspace of multi-person body deformations, and a recurrent neural network that regresses deformations as a function of body shape and a novel motion descriptor. Before going into details, let me give you a brief summary of the basics of our method. Similarly to Simple, our model is built upon linear blind skinning, in which we have the template of an avatar in T-pose, a set of joints with their respective positions and rotations, and some skinning weights that define how the vertices are affected by each joint. The vector of joint rotations defines the pose of the model. The Simple model extends this technique by replacing the constant template by a parametric one. Specifically, the template is parametrized by a vector of shape coefficient, represented as beta, and the vector of pose coefficient theta. Given these two vectors, the template mesh is obtained by computing two blend shapes and adding them to the initial mesh. The first one, which is called the shape blend shape, receives as input the shape coefficients and returns an offset that transforms the shape of the body. The shape vector beta has 10 coefficients, but in our work we only use the one that is more correlated with the amount of soft tissue. The second blend shape uses the pose coefficients to generate some offsets that correct the artifacts of linear blend skinning. Our method extends the parametric template with an additional term, called the dynamic blend shape, which will produce some displacements as a function of a motion descriptor gamma and the vector of shape coefficients beta. It's worth noting that this idea of extending Simple with an additional blend shape has already been explored in previous works, such as Dyna by Pons-Mols et al. And the work of Casas and Otaduy. Our method differs from Dyna in the way we encode motion information to avoid the entanglement problem mentioned before, and also in the architecture used to predict the soft tissue displacement. Meanwhile, the work of Casas and Otaduy is limited to a single subject, so it doesn't generalize to different body shapes. For clarity and consistency, during the rest of the presentation I'll refer to the dynamic blend shape simply as delta. In order to compute the soft tissue displacements, we propose a pipeline that has three main components. The first one takes as input pose information as well as the global translation of the avatar, and generates the motion descriptor gamma. Then we have a recurrent regressor that receives as input the motion descriptor alongside the shape coefficient, and produces some displacements delta. The displacements predicted by this network are encoded in a low-dimensional space, so the last step consists on projecting those encoded displacements to the full deformation space. Let's see each component one by one, starting with the motion descriptor. Different methods represent motion differently, but the general idea is that the vector gamma has to contain information about the current pose as well as the global movement of the avatar. The standard way of representing pose in skinning-based models, such as Simple, is to use a vector of joint rotations, but this representation carries several problems. Since the model contains redundant joints to enable fine control of the pose, this results in an over-parameterized representation. Most importantly, These redundancies make it possible to achieve similar poses by rotating different joints. That means that similar poses can be represented by completely different vectors of joint rotations, which is not ideal for machine learning purposes. Finally, poses obtained from the real world are entangled with subject-dependent information that we would like to remove. In this paper, we propose an alternative pose descriptor that is compact, in which similar poses have similar representations, and subject-dependent information is automatically removed. To build a pose descriptor with these properties, we use a multimodal autoencoder architecture. First, we have an encoder that projects the vector of joint rotations into a low-dimensional pose space. Since we want similar poses to have similar codes in this subspace, instead of reconstructing the joint rotations, we are going to reconstruct the skinned meshes, for which we add additional encoder-decoder networks. Notice that the skinned meshes are all generated with the shake coefficient set to 0, since body shape is not relevant for this task. Regarding the insides of the networks, they all have a single fully connected linear layer followed by a leaky ReLU activation. With all this in place, we define the loss function as follows. We have a term that measures reconstruction error in the direction of the mesh encoder, and a second one that does the same but in the direction of the pose encoder. And here comes the important part. We observe that the static features that we want to get rid of are small deformations that don't contribute much to this loss function. That would not be the case if the loss function was formulated in terms of joint rotations instead of skinned meshes. So, having made this observation, if we choose a small enough size for the subspace, the resulting information bottleneck will automatically remove these features while retaining the overall structure of the pose. In our experiments, we found 10 to be an appropriate size for the subspace. Finally, since training this autoencoder only requires pose information, in addition to the poses from the DINA dataset, we also add many from the CMU motion capture database. The size of the extended dataset is enough to cover most of the human pose space. For visualization purposes, here we show a pose before and after being projected to the pose subspace. The result still maintains the overall structure of the pose, while normalizing certain features such as the position of the hands and the feet. At runtime, we build the motion descriptor gamma by projecting the current pose to the subspace, and computing velocities and accelerations using finite differences. We also include velocities and accelerations of the global translation, represented here as x. This is equivalent to the following diagram, in which the blue boxes represent the previously shown pose encoder. And that's all about the motion descriptor. The next step consists on using the vector gamma and the shake coefficient beta to predict the soft tissue deformation. We do so by training a regressor that has an architecture similar to those of residual networks. In order to account for dynamic effects that depend on previous inputs, we use a gate recurrence unit. During training, we optimize for position, velocities, and accelerations. Regarding the dataset, we have a total of 52 ground truth sequences from 5 subjects, but training on this data leads to overfitting. This overfitting happens because of the previously mentioned dynamic entanglement. Each subject performs each motion differently, and the regressor takes advantage of these differences to account for things that should only depend on the shake coefficient. The solution we propose to avoid this problem consists in augmenting the dataset with motion transfer. To do so, first we train a regressor per subject. Since this regressor is only trained on data for a particular body shape, it can be used to predict how any motion will look on that body. That means that we can feed sequences of other subjects to the single subject regressor and generate synthetic data that can then be used to train a multi-person regressor. For example, if we take another look at the running exercise, after augmenting the dataset, we are going to have data of the 5 subjects performing the 5 variations of the running animation. For instance, here is the synthetic data that we generate for the subject in the middle. This strategy allows us to train a regressor that doesn't overfit subject-specific features and generalizes very well to new body shapes. The final step of the pipeline consists on projecting the outputs of the regressor to the full deformation space. The main reason why we work in a subspace is because of the high dimensionality of the deformations. In the case of Simple, the template mesh has 6,890 vertices, so the displacement vector has that size times 3. Previous work used different approaches to handle this dimensionality. Dyna, for example, uses PCA to find a linear projection to a lower dimensional space. Meanwhile, the work of Casas and Otavi shows that autoencoders can find more compact representations than PCA, but their subspace is limited to the formations of a single subject. In contrast, our autoencoder encodes the formations of multiple subjects in the same subspace. Our autoencoder also uses a different architecture. The figure on the right only shows the decoder part, but the encoder network is very similar. Both networks are composed of 2 residual units, where each unit is a combination of batch normalization, liquid ReLU activation, and fully connected linear layers. Inspired by the recent work of Fulton et al., we initialized the first and last layers of the autoencoder with weights computed with PCA, which improves the conversions of the training process. For the size of the latent space, we choose 50 dimensions, since it's a good trade-off between reconstruction quality and compression. Finally, the autoencoder is trained by minimizing error in the surface and the normal vectors of the reconstructed mesh. This comparison shows that our autoencoder can reconstruct the formations better than PCA. Moreover, the autoencoder is capable of reconstructing high-frequency details, which are important to achieve realistic soft tissue animations. And that concludes the description of the method. For the evaluation, we first test how each contribution affects the overall performance of the model. In the following plot, the horizontal axis represents the body shape, while the vertical axis shows the average vertex speed. For a body shape with a lot of soft tissue, we will expect the vertices to move much more than in the case of a lean body. When training our network without any of the contributions, that is, without augmenting the dataset and using joint rotations to represent the pose, we observed that the model generalizes poorly. Despite the significant difference between the body shapes, the soft tissue dynamics predicted by the naive model are almost the same. When we introduce our motion descriptor with a disentangled pose, the model starts to generalize much better. The same is true if we use the augmented dataset without the motion descriptor. That said, the model performs best when both contributions are used together, which produces the widest range of soft tissue dynamics. For comparison purposes, we also show the results obtained with our implementation of Dyna, which suffers from the same problems as the naive model, that is, very little variability of soft tissue dynamics. Here we visualize the range of soft tissue dynamics produced by our model. As shown in the previous plot, our model produces very different soft tissue dynamics depending on the body shape. And here we use a color map to highlight the magnitude of the soft tissue displacements. We also evaluate the ability of our method to generalize to novel motions. For example, here we compare the results of our method in a test sequence against the ground truth data. When the subject has little amount of soft tissue, our model successfully predicts that the displacement should be small. We also evaluate our method in sequences of different datasets than the one used for training. Note that in this case we don't have ground truth data to compare with. The following sequence is particularly challenging, because the motion is very different from the ones in the Dyna dataset. Nevertheless, our method manages to produce plausible results. We also show an interactive demo of our model. The full runtime pipeline runs on GPU at more than 200 frames per second. To wrap up, we have developed a method that produces realistic soft tissue dynamics, generalizes well to new shapes and motions, and runs at interactive frame rates. That said, there are still several limitations that would be nice to address in future work. Due to the limited amount of data, our model is limited to one shape coefficient, so it would be interesting to explore alternative approaches that enable sampling a larger shape space. Furthermore, our model is limited to the template of the simple model, so currently it doesn't support variable topologies. Finally, we believe that adding interaction with external objects will also be a very interesting line of future work. I'd like to end this presentation by thanking the funding agencies and all those who helped in this project.
Thank you for a very nice presentation. And now we are ready for some questions. So I'll just see if there are some questions. Igor, have you tried to overcome the limited data sets by running full simulations on animated models?
No, we haven't tried that. The problem with physical simulation would be that it is slow, so generating a large data set would be quite time consuming. So we decided to use the one that was already available. Also, since the dataset we use is based on real world data, that enables us to achieve realistic results.
Okay, thank you. Let's see if there are more questions. Otherwise, I would have one for you. I was wondering about the motion descriptor. As I understand that you use this post descriptor as part of that, and you choose a dimension that you said equal to 10. And I was wondering what is the meaning of that? Is it just an abstract notion? And how come you use the dimensionality 10 for that?
Yeah, the dimensionality controls how generic the descriptor is. If it is very high dimensional, the motion descriptor will capture fine details in the pose, like the rotations of the hands and things that are not really relevant for this problem. So by choosing a size of 10, the information that is encoded in that latent space is not very generic. It describes how the arm is raised or if the leg is raised, but it's not. It removes the particularities that each subject has in those motions.
Okay, thank you. So without further ado, I will introduce the next paper in this session. And the next paper is entitled Modeling and Estimation of Nonlinear Skin Mechanics for Animated Avatars. And it's written by Christian Romeo, Miguel Ortudue, Dan Casas, and Jesus Perez, and will be presented by Christian. Please go ahead.
Hello, my name is Christian, and I'm here to present you our work entitled as Modeling and Estimation of Nonlinear Skin Mechanics for Animated Avatars. To start with this presentation, let me first motivate our work. For an accurate depiction of humans in virtual environments, realistic animated avatars are essential. In addition to the fields of virtual reality, video games, and VFX, where human avatars have their main application, new and exciting possibilities are currently appearing in areas related to virtual try-ons and garment design. Handling accurate soft tissue deformations is a key property for the construction of any realistic avatar. In this work, we present a soft tissue avatar model which shows highly dynamic effects and realistic external interactions. Most of the related works in the research community can be classified in two groups: physics-based methods and data-driven methods. Physics-based approaches are mostly based on physical laws. They have good generalization capabilities, reproducing by construction a wide range of soft tissue deformations and supporting external interactions. As a drawback, the precise reproduction of observed real deformations is challenging. This forces the construction of extremely complex models and parametrizations to replicate the real human anatomy. Also, physical simulations are generally a slow process. Data-driven methods, instead, are constructed directly from real soft tissue deformation data, being free of any physical constraint. The main disadvantage of these approaches is their poor generalization capabilities, complicating the reproduction of unseen deformations and external interactions. However, as a key feature, observed deformations can be accurately reproduced. And due to the low computational cost, fast real-time responses can be achieved. A novel example of a data-driven model is introduced by Santesteban et al., whose work is also being presented at this Eurographics conference. The avatar model we present in this work belongs to a third group of hybrid methods. These approaches combine features of the two previous groups, trying to preserve the good properties of both. In the work presented in 2017 by Kim and colleagues, the potential of this hybrid proposal was evidenced. As in the work by Kim et al., we first construct a hybrid avatar, combining a data-driven avatar model and an FAM soft tissue simulation. This avatar is characterized by two sets of parameters. The kinematic behavior is characterized by shape parameters describing the body constitution and pose parameters controlling the skeletal pose of the avatar. The mechanical behavior is characterized by soft tissue thickness and material properties at different points in the body. We estimate these parameters starting from a set of different captured animations of a particular subject. Comparing the results of the simulated avatar with the real captures, thickness and material properties are estimated, trying to match the animations. More specifically, error metric is minimized between simulated and captured vertex trajectories, using this error in an optimization procedure to estimate the mechanical parameters. Notice that shape and pose parameters need to be estimated also. On this work, we are focused on mechanical estimation, using the approach of previous works to obtain shape and pose parameters. We have made contributions at important stages of this pipeline. Specifically, we contributed in three important points. Starting from the data-driven avatar, we propose a method for the generation of a soft tissue layer, ensuring a smooth discretization even for thin cases. This soft tissue layer is simulated using an elastic FAM, while we propose a novel elastic deformation metric and a custom anisotropic nonlinear material. Thanks to the alternative deformation metric, we preserve all the surface details of the data-driven model when the avatar is in static poses. With the custom material, we improve capture fittings and external interaction capabilities. Finally, in the parameter estimation process, we minimize a novel anisotropic variance error metric on surface vertices. Measuring anisotropy is important for the correct estimation of the anisotropic material properties. From now on, I will give you a more detailed explanation of these contributions. So, let's start introducing the way we construct the soft tissue avatar. Our model takes Simple as a starting point. Simple is a parametric avatar model presented by Loper and colleagues, with the capability of creating accurate static surface deformations. Starting from the rigged template mesh with the corresponding joints and skinning weights, the method deforms its vertex with a combination of corrective plane shapes and traditional skinning. Plane shapes and joint locations are learned from 3D human captures in different poses. The final deformation is controlled by shape parameters describing the body constitution, and pose parameters controlling the skeletal pose of the avatar. For the generation of the soft tissue layer, we start from the simple template mesh. First, we remove the extremities, considering the soft tissue layer irrelevant in these body sections. After removing the extremities, we shrink the surface towards the rig. The space between the external and internal surfaces allows us to define a soft tissue layer, but the per vertex thickness of this layer is a parameter of our model, and later we will show how we estimate it. The direction of rho of the thickness layer are determined as the solution of a projection smoothing iterative process. We refer to the paper for a more detailed explanation of this point. Having the internal and external surfaces at the soft tissue layer, we merge both of them at the boundary, obtaining a closed surface. Inside this closed surface, a volumetric mesh is generated, ensuring that the external vertices are preserved. Finally, having all the original simple quantities defined just at the surface, we interpolate into the generated volume using Laplacian interpolation. At this point, we have a completely equivalent volumetric version of simple, and any of the new volumetric vertices can also be skinned. Notice that our method ensures a smooth internal surface, being this an important property for the robust simulation of thin soft tissue layers. Now, I am going to explain our soft tissue mechanics approach, starting from our alternative deformation metric. Just for explanation purposes, let me use this arm to represent the new volumetric simple. Starting from this volume, we construct an elastic FAM deformable with the same topology. In the same way the simple avatar can be kinematically skinned to a particular pose, the FAM deformable can also be transformed. But in this case, just the internal red nodes are controlled by the skinning, driving under pose changes the simulated nodes represented in blue. At this point, we can make an important observation. The external surface of the FAM avatar is exclusively determined by the simulation, not by the simple model. For a static avatar pose, surface nodes tend to the less deformed configuration, minimizing the total elastic energy. As a consequence, the surface of the simulated avatar usually does not coincide with the surface of simple. One can assume that a mechanical parameter estimation can help us reproducing the realistic simple surface deformations. However, due to the complexity of the original human anatomy, matching exactly the data-driven model is an extremely and perhaps unsolvable problem. To preserve the surface detail of simple for static poses, we propose an alternative deformation gradient. The standard deformation gradient for a given deformed shape is defined as the derivative of the world space position x with respect to the material space position X. Our alternative deformation gradient removes the influence of the current avatar pose. Starting from the deformed shape, we first unpose it applying the inverse skinning function, obtaining as a result the unposed shape. Then, the deformation gradient is computed in the new shape, deriving the unposed position with respect to the material space position. With this new metric, we ignore static deformations already considered by the skinning, focusing instead on local high-frequency deformations. As you can see in this side-by-side comparison, our deformation gradient matches simple for static poses. This property is important, given the precise static deformations already captured by the data-driven model. Now, I'm going to introduce our anisotropic nonlinear material. We propose hyperelastic material whose elastic energy density is constructed as follows. Our starting point is the isotropic St. Bernard-Kirchhoff material. This energy has two terms. The volume term controls how incompressible is the material. The stretching term, instead, controls the resistance and the longitudinal deformations. We added two important modifications to this last term. First, observing a strong directionality in unposed vertex trajectories and motivated by the layered structure of skin, we support orthotropy in our material, weighting the strain resistance differently under different orthogonal directions. This anisotropic property is parameterized by the normal and tangential elastic modulus, together with the basis, which is aligned with the normal of the avatar surface. Notice how, using just a single tangential modulus in our parameterization, the elastic properties are equal in R inline directions. Also, to reproduce the kick transition of a scheme from soft to stiff, we extended our material with a func nonlinear stress-strain relationship. This nonlinearity is controlled by a saturation parameter, which is fixed to a reasonable value. In this comparison, you can appreciate the effect of this nonlinearity. For the same light weight, our material and the Neo-Hookean one are equally deformed. However, notice how the deformation of our material saturates under the effect of heavier weights, showing a higher nonlinear response compared to the Neo-Hookean one. The described energy density allows accurate simulation of soft tissue dynamics and external interactions. Let me now describe how we estimate the parameters of our model. As input of the estimation, we use the dataset presented in the DYNA paper by Pons, Moll and colleagues. This dataset is composed of surface 4D captures of different human subjects performing different action sequences. The topology of the meshes is identical to this of SIMPLE, allowing a one-to-one vertex correspondence. Starting from this dataset, we estimate the shape and pose parameters for each subject and sequence, following the approach described by Casas and Ottadui. After unposing both captures and simulations, we minimize an error metric in this space. As previously stated, we observe on captures a strong directionality in unposed vertex trajectories. Based on these observations, we introduce a novel error metric using the anisotropic motion variance of unposed surface vertices. In this slide, you can see how this anisotropic metric is computed. Given the unposed trajectory of a surface vertex, we first obtain its mean position. Then, taking this position as the origin, the trajectory is projected to the normal vector of the surface and its tangential plane, computing the normal and tangential variances, respectively. Repeating this computation per vertex, we obtain a vector representing the anisotropic variance of a particular sequence. The residual between captured and simulated sequences is a metric of how similar they are. Based on this anisotropic residual, we pose the estimation as a least square optimization problem for each subject, minimizing the sum of squared residual norms for different sequences. To take advantage of the least square structure of the error, we used a Gauss-Newton type solver. And due to the complexity of the simulations, the Jacobian of the residual is computed with finite differences. The nature of this problem allows certain accelerations. First, assuming a smooth parameter distribution, we specify the values at a reduced number of surface control points, interpolating the parameters to the rest of surface and volume. This can be a huge reduction in the number of parameters to be optimized. Even more, being the human body right-left symmetric, we estimate just half these control points, later mirroring the results. In the image, you can see the influence area of one of these control points with the corresponding mirroring applied. As a second acceleration strategy, we observe that the trajectory of each of the deformed vertices depends only on the mechanical parameter distribution in a closed neighborhood. This implies that the Jacobian of the residual has a sparse structure. We propose a heuristic to obtain this sparsity information, using it later in finite different computations to approximately halve the optimization times. In the right image, the point in the chest is estimated to be influenced by the material properties in the bluish zone. We refer to the paper for more details on the generation of the sparsity pattern. Having explained the details of our soft tissue avatar, let me show you some of the results. To prove the flexibility of our proposal, we have estimated the parameters of the model for 3 different subjects from the DYNA dataset. For the estimation of each of these subjects, we used 2 different capture sequences. Starting with 12 parameter control points, the optimization is extended to 42 points after convergence, initializing their value with the previous results. To avoid redundant effects of layer thickness and material stiffness, we separate both sets of parameters and follow an alternating optimization chain. In these animations, you can see for each subject a side-by-side comparison of one of the captures using the estimation and the corresponding simulated results. We also test the estimated model with sequences not used for the optimization. Notice how our model, just using 2 sequences for the estimation, can properly generalize to unseen sequences. In these color maps, you can appreciate the tangential and normal errors for estimation sequence of one of the subjects. Realize how, comparing with simple, both errors are reduced with our soft tissue model. And here the same results for a test sequence. Comparatively, in both estimation and test sequences, the reduction in tangential error is more noticeable. We proved the external interaction capabilities of our model with some simulation examples. In this slide, we compare our constitutive material to the stable neo-Hookean material presented by Smith et al. In both cases, parameters are estimated from real captures. As you can appreciate, the avatar has a weight hanging from the belly, shaking the hips at the same time. Notice how the elongation amplitude of our material saturates, showing a higher nonlinear response compared to the neo-Hookean one. To demonstrate more complex and challenging external interactions, we have integrated the ArcSim clot simulator with our soft tissue avatar, implementing the bidirectional coupling. In this animation, the avatar is wearing tight clots, with noticeable soft tissue deformations in the biceps and belly area. These deformations are very far from the observed data used for training. However, our nonlinear and orthotropic material behaves well even under tight compression. In conclusion, we have presented an hybrid soft tissue avatar model with desirable features of both physics-based and data-driven approaches. In this process, we have found some limitations. Due to the cost of a single error evaluation, the parameter estimation for each avatar takes long time, so we cannot afford optimizations with much more parameters. With 42 control points, as used in our results, the estimation takes from 30 to 40 hours, depending on the subject. Also, we have observed a trade-off in the material between anisotropy and volume preservation. This prevents us from using a near incompressible material if we want to conserve the good fitting results of the captures. Solving these limitations is an appealing direction of future work. On the positive side, our proposal has the next important novelties. We preserve the surface of the statistical model for static poses, ensuring realistic static deformations. Also, we use a custom constitutive material that captures the nonlinearity and anisotropy of the skin. The importance of these properties is proven, both for correct representation of the captures and for realistic external interactions. Finally, our parameter estimation is based on a novel anisotropic variance metric, a key feature for the estimation of anisotropic materials. Overall, we have shown that our method is capable of realistically modeling soft tissue avatars under highly dynamic effects and extreme external interactions. We thank the funding agencies and all those who help in this project. Thanks.
Thank you for a nice presentation, and now we are ready for some questions. So I have a question. I was wondering how sensitive realism is to the accurate modeling of the soft tissue layer, or whether the whole parameter estimation basically takes care of that, and how that would relate to a real biomechanical model of a human.
Okay, the first question was, I can answer the second one. The idea in our work was not just getting an exact model of because this is exactly what we are not trying to do, because we think that if you go to an extremely anatomical approach, you fall in a pure data-driven method. So in these cases, the parameterization can be extremely complex. estimation. So what we did is just take an in-between approach, and our idea is just getting a visually plausible results under dynamic movements and external interactions. So this is why we choose an isotropic material to more or less capture the wide range of behaviors. We don't need an internal structure to describe all the anatomy of the human body.
Okay, thank you. Could you elaborate a little bit on how you added collisions and self-contact to this system?
Yes, I can elaborate. Our model by itself doesn't have collisions, but we added the ArcSim cloth simulator. We added a bidirectional coupling in it to handle collisions. And at this point, we used the internal collision system of ArcSim. So it was in some way automatic once we do the work of integrating the bidirectional coupling.
Just a little follow-up question on this. Did it have any issues for the learning process when you deal with non-smooth events or something like that?
What do you mean non-smooth? At which point of the...
I was thinking by when you have contact, for instance, with things or snagging or stuff like that going on in the animations, whether that would create...
Do you mean in the estimation or in simulations?
Well, I guess you would. I'm not sure.
Yes, but maybe because in the cloth simulation just was for testing the external capabilities, while we didn't do any training with the cloth, with the bidirectional coupling with cloth. So in the case of estimations, we just did it with the clean model without any cloth or external interaction.
Okay, I see. Thank you for clarifying that. And thank you for the presentation and the answers. So now we're ready to go on for the next paper in this session. And the next paper is entitled A Practical Method for Animating Anisotropic Elastoplastic Materials, and is written by Camille Screg and Chris Voiton, and Camille will do the presentation.
Hello everyone. My name is Camille, and today I am going to present to you our method for animating elastoplastic material with a strong anisotropic behavior. At the beginning of this project, we wanted mostly to animate big piles of leaves or branches, or maybe even large piles of any kind of objects, because you will never know when you need to model a big stack of giant food collapsing. We wanted to focus on a scale large enough that it's not possible to represent the material by modeling each object. At this scale, the motion of each object, particularly inside the pile, doesn't really matter anymore, and we are more interested in the general behavior of the material. This kind of material is going to act more or less like sand, with weirdly shaped grains. And a method that has been quite successful to model sand and granular material recently in computer graphics is the material point method, as you can see, for example, on these nice pictures from the article of Clar and colleagues and Davier and colleagues. So let's first take a closer look at MPM, before focusing on our objectives for this project, and then get into the technical details of our method. Right. MPM was first proposed in the physics domain by Sulsky in 1995, so relatively recently for physics, I guess. It has been then introduced in computer graphics by the Snow paper from Stomaking and colleagues in 2013, and had been then used to represent foam, jello, and a lot of different, highly deformable materials. This method works well for this kind of material, as it doesn't use any mesh, but represents the material as a continuum. It actually uses a hybrid representation, both Eulerian with a grid and Lagrangian with particles, each particles representing part of the continuum rather than a specific grain. So let's take a quick look at the pipeline of this method. We have part of the computation happening on the grid and part of it on the Lagrangian particles. Each particle has some physical states, mass, velocity, deformation and stress represented as matrices. At the beginning of the simulation loop, the masses and velocities are interpolated on the nodes of the grid. Then forces are computed on each node, before updating the velocities. If necessary, collisions can also be handled on the grid. Then the velocities are interpolated back on the particle and the deformation is updated. We can then apply a constitutive law on the particle. This law is going to define the physical behavior of the material. In our case, we use an elastoplastic law, where the elastic and the plastic behavior are separated into two different steps. First, the elastic stress is computed from the deformation. This can potentially put a particle in a physically unfeasible state, in which the material should break or deform plastically. To correct this, a plastic step is then applied to project the stress and the deformation back to a feasible state. Finally, the particles are advected and the loop can start over. During this presentation, we are going to focus on the steps where the constitutive law is applied. So let's get into them a little bit more in detail. Right, first the elastic law. During this step, the stress is computed as a function of the deformation. So here sigma is the Cauchy stress, and E is the green strain that can be computed from the deformation gradient f. There are several ways to define this function. Here are a few of the most popular ways to do this. A hyperelastic law defines the stress as the derivative of an energy function of the strain. So here S is the second Piola-Kirchhoff stress. Cauchy stress can be computed using this formula. For linear material, the stress is simply computed by multiplying the strain by a first-order tensor C. So each component of sigma are a linear combination of the components of E. The tensor C must be symmetric, so it has 36 degrees of freedom. This can be reduced if the material behavior exhibits some symmetries. For example, for an isotropic material, C is entirely defined by a Young modulus and a Poisson ratio. Another example would be an orthotropic material, so a material that has 3 planes of symmetry. This material would be defined by 9 coefficients, a Young modulus, a Poisson ratio, and a shear modulus for each plane of symmetry. Right, now that we have seen a few of the possible elastic laws, let's go to the plastic step of the pipeline. As I said before, after the elastic step, the stress and the strain can be in a physically infeasible state. The plastic law defines the feasible state using a yield surface. The yield surface is defined by a scalar function of the stress and the strain. The admissible state is where the yield function is inferior to 0. If f is superior to 0, the plastic deformation is created by projecting E and sigma back onto the yield surface where f equals 0. A simple example would be the plastic model used by the snow paper from Stomaking. The eigenvalues of the strain are simply clumped to an interval. So if the snow is too much deformed in any direction, so it gets out of this blue region, it starts breaking or being packed. So clamping the eigenvalues puts the state back onto this blue square. Another example would be the Drucker-Prager model, which would be the equivalent of the Coulomb friction for granular material, such as sand. This method has become quite popular in computer graphics, and a lot of work has been done to expand its possibilities. But still, it's mostly isotropic material. But if we want to model a material composed of non-spherical grain, like this for example, the behavior of the material is going to depend a lot of the orientation of the grains. So if like this, all the objects are oriented in the same direction, the material is going to be strongly anisotropic. So we wanted to try and make MPM anisotropic. How can we do that? It's not very complicated. We can just find or create the right constitutive anisotropic law and just apply it. But the law working for woods, for example, may not work for another kind of material, like a stack of papers or rice. So why limit ourselves to piles of objects after all? Why not try also fibrous material, for example? So we decided that we wanted also the method to be very general, and to really let the user explore by themselves and define whatever anisotropic behavior they want. So we inspire from this physics article from Carr and colleague. They propose a model for fibrous reinforced material, like cement or concrete. And what they propose here is to map the stress and the strain into a fictitious isotropic space, apply some isotropic laws there, and then map back to the real anisotropic space. A similar idea can be applied to MPM. Let's just solve the problem in a fictitious isotropic space, so we can easily use the usual isotropic laws and then reuse the existing MPM code. The anisotropy will then be defined by the mapping. Now let's see more in detail how we have to change MPM to achieve that. So first we associate a mapping to each particle as two fourth-order tensors, A sigma and IE, that are respectively mapping the stress and the strain. So here we can go from the real anisotropic space to the fictitious isotropic space just by multiplying the stress and strain matrices by the tensors, and then map back with the inverse tensors. The anisotropy direction depends on the orientation of the material, so we need also to know the rotation of the particle, so we can apply the mapping in the local frame of each particle. So now we know how to map the stress and the strain for each particle, and switch between the real anisotropic space and the fictitious isotropic space. Now let's see how the MPM pipeline is actually modified. We need to know the rotation of each particle. That's not very complicated, there are several possibilities to do that, using a decomposition of the gradient deformation, or using the velocity on the grid. Then we have our fictitious isotropic space, and we want to apply the constitutive law there. So for this, we just need to map the stress and the strain as we saw before, like this. Now these elastic and plastic steps are the same as for the isotropic MPM. The only thing changing is the addition of the mapping steps before and after them. Right, now you are probably wondering how we are defining these maps, A sigma and IE. Well, they must be symmetrics, but apart from that, they actually can be chosen arbitrarily. So that's 36 parameters to choose for each. So we started playing with this, and just kept AE as an identity, and chose some random parameters for A sigma. We tested it on a collapsing column, and here is the kind of results we get. So it's nice enough, and it's very fun to play with, but it's actually very hard to control the behavior with these parameters. So we decided to reduce the number of degrees of freedom and limit ourselves to an orthotropic material. We chose only 3 parameters that define A sigma. These parameters are going to stretch the stress along 3 axes and control how plastic the material is along this axis. We can then compute AE with this formula, where C and C bar are the elastic tangent of the elastic laws in the real and fictitious space. So C bar can be computed by linearizing whatever isotropic law you choose to use. And as we are using orthotropic material, we are choosing C from the linear orthotropic elastic law. So by doing this, we are limiting the range of behaviors possible. But now we have only 12 parameters that are a little bit more intuitive to navigate this complicated space. Here are some results. For this example, we are collapsing a column of material and changing only one of the plastic coefficient A1 to control in which direction the column is going to collapse. So here is an isotropic material. And then we are adding some anisotropy. And then a stronger anisotropy. We can then go for more complicated examples. In this video, we try to represent different kinds of material. Here we have some flat grains, like cards for example. Now some elongated grains, like roads. And here I don't remember what I was trying to do, but I just liked the results. And now we have the same materials, but with the initial grain tilted. To try to get more compelling results, we added 2 extensions that are kind of preliminaries for future works. We propose a method for improving the visualization of the grains, and then a method to model the mixing of the grain and how their orientation is changing due to internal interaction and collision. So for the visualization, MPM's particle represent part of the continuum, which can include several grains. To take that into account, and also to visualize the orientation of the non-spherical grain, we represent each grain as a subparticle with a position and an orientation. The subparticles do not influence the simulation, but are just advected and rotated using the velocities on the grid, in the same way that the MPM particles are advected. If a subparticle reaches a region where the density is too low, so where the velocity is not well defined anymore, we just give them a ballistic motion. This enables us to improve the rendering of our simulation by representing a number of grains much larger than the number of MPM particles. The second extension is a way to model the mixing of the particle. So one particle usually represents several grains, and the anisotropy of the material is going to depend on the orientation of the grains. As these orientations change over time, so should the anisotropy, which means that the mapping tensors should be updated. So we represent the general orientation of the objects for one particle with a matrix π2, which is the second moment matrix of the distribution of the orientations. The eigenvectors of π2 represent the main orientation of the grain. And then we update this matrix over time using this formula, where d and w are the symmetric and asymmetric part of the velocity gradient, and L is a coefficient describing the elongation of the grain. This formula is usually used for fibers in suspension in a flowing fluid. So we have a rotation part, where the objects are just rotated with the flow, and a deformation part, which takes into account the grain's tendency to align with the flow, and also the collisions between the grain. These formulas seem to be a valid approximation of what's happening inside the pile, but further studies will be required to really understand the mechanism inside the material. Now that we have a representation of how the orientation is changing, we can use it to modify the anisotropy. We are doing this in a heuristic way by observing that when the three eigenvalues of π2 are equal, then the orientations are uniformly distributed, and the material can be considered as isotropic. If two of the eigenvalues are zeros, then all the grains are oriented in the same direction, and the anisotropy will be maximal. Then we are just interpolating our parameters between these two states. Let's see what we can get with this extension. Here are some particles flowing on a tilted plane with two obstacles, with and without the mixing. We can see that the behavior is slightly different, and in the simulation with the mixing, the grains tend to align more with the flow. To finish, we have some more results to show you. In this video, we are stretching a bar of fibrous material. According to the orientation of the fiber inside the material, the behavior is going to be different. And now we have the same material, but the bar is being bent. And finally, a video of a truck dumping some objects. As before, the behavior is going to be different according to the orientation of the objects. To conclude, we obtain a wide range of possible anisotropic effects, while reusing usual isotropic laws and with minimal modification of the MPM code. But the two extensions I showed are still in a very early stage and will require much more work and studies. And another big problem is that it's very difficult for now to find the right parameters that would correspond to an actual physical material. Solving these problems would make some interesting future works. Now, if some of you are interested, our code should be soon available on GitHub. Thank you all for your attention.
Thank you for a very nice presentation, and we are now ready for taking a few questions. And I think I would like to start with the first question. So I was wondering how close the results are to reality. Have you thought about how to investigate this?
So we thought a lot about this, but it's first really hard to find the right parameters to match reality. And given that the really nice behavior are when all the objects are oriented in the same direction, it's also very hard to set up an experiment, a real experiment to compare. So we tried something with some pasta cut in small parts. I tried to align them in a box and remove the box, but it wasn't, well, we had 1 or 2 videos, but it wasn't good enough to put in the result. And it was very long to set up just 1 video for this. So it's still kind of future work to really find a good way to do the experiment for this.
Okay, thank you. I was also wondering about, the AE and ASIMA maps. I understand the idea of creating some low-dimensional mapping that is easy to control for an artist or a modeler. But I was also wondering about, how to push this further. How could one get some, mappings that would be inspired perhaps by real materials? Is this something that you have been thinking about?
Well, as before, it's still mostly future work. So, we can think about some data learning or something like this to find the real parameters. But still no brilliant idea for this yet.
Okay, thank you. Just one last question. The fracturing and the small debris that breaks off the materials, how did you do that?
So I talked about it kind of very quickly in the presentation. So with NPM, where there is only few particles in one grid, it's usually not working very well. So when some of our subparticles are going too far away from the bulk material, we just give them some very simple motion with the initial velocity they had and the gravity, and just give them some ballistic trajectory, which gives us these fibers flowing away sometimes.
Thank you for your answers. Very nice work. And I would now like to introduce the fourth and last paper in our session, and it's titled Mixing Yarns and Triangles in Cloth Simulation. It's written by Jon Casafranca, Gabriel Ziro, Alejandro Rodriguez, Ida Miguel Otodui, and will be presented by Jon. Please go ahead.
Hello, and welcome everybody to this video presentation of our paper Mixing Yarns and Triangles in Cloth Simulation. This work has been done by Gabriel Cirio, Alejandro Rodriguez, and Eder Miguel from SEDI Labs, and by Miguel Otadui and me, Juan José Casafranca, from University Rey Juan Carlos. The classic approach to cloth simulation is to use triangle-based models. They consider cloth as a continuum surface, discretizing it using a triangle mesh. The discretization can be adapted based on the computational needs or the level of detail required by the application. There is also the possibility to modify the discretization at runtime, adding or removing triangles where needed. However, triangle-based models lack the accuracy and expressiveness needed for the extreme realism. Nonlinearity, anisotropy, or internal friction require complex constitutive material models. On the other hand, Young-level models have emerged as an alternative for the simulation of cloth with extreme realism and detail. They reproduce by construction the structural nonlinearity and anisotropy of fabrics, and they support plasticity intrinsically. However, they are not free of cost. Discretizing a common garment at the Young level may require millions of nodes, and therefore large computational cost and large memory. This example compares triangle-based and Young-level simulations on the same chart. Both are rendered at the Young level, but, on the left, we have used a triangle-based model for the simulation. The detail provided by a Young-level simulation is evident in some regions, but others remain smooth, and a triangle-based simulation is sufficient. In our work, we propose a method to mix yarns and triangles in the same simulation. We let the user choose regions of interest where Young-level detail is important, as shown in red on the left, while the rest of the garment is simulated using triangles. To avoid artifacts produced by a hard transition, we use a blending region where both representations are combined. As I will show later, this is possible thanks to novel formulations of enriched kinematics and dynamics. We initialize the simulation with the triangle-based result, and then we insert yarns in the regions of interest. In this example, we choose the armpit area as region of interest, as it suffers high tension. We execute the mix simulation as a relaxation, and interesting details appear in the armpit area. These details are well captured by our mix simulation. Our method can use pretty much any mechanical model for triangles and yarns. In our implementation, we have used St. Bernard-Kirchhoff and discrete cells for the triangles, and the persistent contacts model of Sirian collects for the yarns. Our work is divided into three main technical contributions. First, we propose a kinematic representation that enriches a triangle mesh with local yarn-level details. Second, we derive a smooth blending of triangle-based and yarn-based mechanics equations. And third, we present an efficient solver for the resulting system of equations. In the following section, I will explain the mixed kinematics to represent cloth simulation in hybrid regions. Let's take a node in a yarn and its embedding triangle. We compute the barycentric coordinates of the yarn node with respect to the triangle. When the triangle moves, we track the position of the yarn node inside the triangle using the barycentric coordinates. We call this yarn node position the base position. Now, let's add a detailed displacement to the yarn node. So, the wall position of the node can be computed as a combination of the base position and the detailed displacement. But there is one problem. The representation is not unique. Infinite combinations of triangle positions and yarn displacements produce the same wall position of the yarn node. To remove the redundancy, we must add some constraints. The common approach is to formulate the equations of motion using constraint dynamics, but this adds a large overhead to the simulation. Instead, we embed the constraints in the kinematic representation using a kinematic filter. The idea of the kinematic filter is not new, but we introduce a general and sound derivation of both the filter and the resulting equations of motion. Let us define a matrix F that acts as a kinematic filter on the detailed yarn displacements. It is a projection that removes from X as many degrees of freedom as those present in B. But we want to choose a good F. We seek one particular filter F such that hybrid regions can be seamlessly coupled to triangle-based regions. To do so, we pose the condition that yarn displacement must represent only what base positions cannot do. This is achieved by making the filtered yarn displacement orthogonal to the base triangle displacement. From this condition, we derive the equation for the filter, The resulting filter is a projection of the yarn displacement to the null space of the base position. It is low rank and constant. It depends only on the barycentric coordinates. This example compares our enriched kinematic model. At the left, a square patch is simulated using yarns, and at the right, the same patch is simulated using our enriched kinematic model. The motion of both patches is the same. Now, I will explain how we obtain the equations of motion for our mixed representation. This section is divided into two parts. First, I will show a generic derivation of the equations of motion for filtered kinematics, and next, I will show how we define kinetic and potential energy that mix triangles and yarns. To derive the equations of motion, we use the Euler-Lagrange equations. First, we need to define the generalized coordinates. The generalized coordinates are a set of independent and non-redundant coordinates that represent the state of the system. In our case, the triangle vertices and the yarn displacements are redundant, but when we add the kinematic filter, they become non-redundant. Therefore, S times Q represent our generalized coordinates. Here, we use the generalized filter S. Second, we define the kinetic energy of our system. As I will show in a minute, the kinetic energy combines energies defined at triangle level and at the yarn level. Similarly, the potential energy also combines triangle level and yarn level energies. By applying the Euler-Lagrange equations with these definitions, we obtain the equations of motion of the system, which define the accelerations of generalized coordinates as a function of forces. These equations resemble the typical equations of motion for unconstrained dynamics, but in our case, they are pre-multiplied by the filter S. In a nutshell, we obtain a filtered version of the unconstrained equations. Now, I will explain how we obtain the total kinetic energy and potential energy of our system. We define a scalar blending field, alpha, over the complete simulation domain. Regions with an alpha value of 0 use a triangle-based representation, while regions with an alpha value of 1 use a yarn-based representation. Blended regions use our enriched representation to enable a smooth transition. Thanks to this blending field, we can blend triangle-based and yarn-based energy densities. At every point of the cloth object, and for every type of mechanical energy, such as elastic or kinetic energy, we define two energy density functions: a triangle-based energy density, which depends only on the triangles, and a yarn-based energy density, which, due to the enriched kinematics, depends on the triangles and also on the yarn displacements. By integrating the weighted energies over the cloth domain, we obtain the total energy. Conceptually, this is a blending of the triangles and yarn energies. We applied this energy blending definition to the kinetic energy of triangles and yarns. The total kinetic energy is therefore a blended sum of the kinetic energy of triangles and yarns. Through the Euler-Lagrange equations, we obtain a generalized mass matrix, filtered by the generalized filter S. Let's look at the block structure of this mass matrix. The triangle mass contributes only to the triangle term, but the yarn mass contributes to the yarn displacement term, to the triangle term, and to cross terms, due to the enriched kinematic representation. We follow a similar process for the potential energy, which is a blended sum of triangle-based potential energies and yarn-based potential energies. Taking the gradient with respect to the generalized coordinates, we obtain the generalized forces of the system. Again, triangle forces affect only the triangle term, while the yarn forces affect both the triangle and yarn terms. The full details of the equations are given in the paper. As shown in this example, our enriched dynamics produce a smooth transition between yarn details and a coarse triangle simulation. In the example, a cloth patch is stretched and sewn to a larger patch. Fine wrinkles appear due to compression, but a triangle-based method fails to capture them correctly. By adding yarns on the seam, we are able to improve the result. wrinkles are now very similar to the full yarn-based solution. Now, let us look at how we solve the enriched dynamics equations. We discretize the equations of motion using backward-Euler, and we use Newton's method to solve the resulting nonlinear equations. Each Newton iteration requires solving a linear system of this form. At first sight, the system of equations looks like the regular system in implicit integration, multiplied by the kinematic filter, but it poses two challenges. One is that the system is not full rank due to the filter. However, Baraf and Witkin showed that this can be handled efficiently with a modified conjugate gradient solver. But there is a second challenge. As shown in this example, a square patch of cloth is pinched at two corners and should fall under gravity, but the simulation suffers numerical damping. The regular conjugate gradient solver measures residual interchange of momentum. As the mass of triangle terms is several orders of magnitude larger than the mass of yarn terms, the conjugate gradient solver is strongly biased to reduce only error on the triangles. Our solution is to rewrite the system of equations in terms of velocities by multiplying by the inverse of the mass. In practice, this is equivalent to using a preconditioner on the conjugate gradient solve. However, this is not an easy task. One may be tempted to use the mass matrix as preconditioner, but this doesn't work correctly, as shown in the following example. In the system of equations, the mass matrix is filtered, so using the mass matrix alone as preconditioner is not enough. The numerical damping is even worse. Recall that the filtered mass matrix is not full rank, so we cannot use it directly as a preconditioner. To design a preconditioner, we can augment the system with the null space of the filter, as proposed by Moxerman. As we saw in the following example, this preconditioner solves the issue with numerical damping. This preconditioner must be applied at each iteration of the modified conjugate gradient solver. We have derived an efficient operation that decomposes the preconditioner into a block diagonal matrix and a low rank update. The full details are given in the paper. Now let's take a look at some additional results that mix triangles and yarns. Thanks to yarn enrichment, yarn-level plastic effects can be introduced in a triangle-based simulation. In this example, a cloth patch is enriched with yarns along the diagonal. We pull from two corners, and inter-yarn friction produces local plasticity. The patch fails to recover the original shape. In this other example, we pull a woven patch from adjacent yarns in opposite directions, and produce yarn-level plastic yield. The effect is captured smoothly with yarns placed only close to the high-tension region. Here, we show a dress simulated using triangles. The dress suffers high tension in the chest area, so we resort to our mixed representation, with the chest as the region of interest. We simulate the relaxation process combining yarns and triangles, and wrinkles appear in places with high tension. Let's look at a close-up of the region of interest. Again, we initialize the dress with the triangle-based simulation, and then we execute a relaxation with our mixed simulation. When yarns are inserted in place of the triangles, extra energy is added to the system, but this energy is relaxed and detailed wrinkles appear. Here, we compare the result produced by our enriched simulation and the result produced using RSIM with triangle remeshing. In this case, RSIM fails to capture the wrinkles of our mixed simulation. Let us look at some data of our latest simulation examples, the shirt and the dress. With realistic yarn densities, the full yarn-based models have more than 2 and 3 million nodes. This leads to very large simulation cost, but also large memory. With a matrix-based implementation, the shirt needs more than 13 GB of memory. It doesn't even fit in our efficient GPU implementation. For our comparisons, we had to resort to a less efficient matrix-free implementation, but even then, the models needed more than 2 and 3 GB of memory. With our mixed simulation method, we slash both the memory use and the simulation cost. In the dress example, the speedup is 25, and the memory used with the mixed simulation method is below 400 MB in both examples. An important requirement for the speedup is that the resolution of triangles is notably coarser than the yarns, for the efficient computation of the filter and the preconditioner. In our examples, the ratio of yarn nodes to triangle vertices in the hybrid regions is of several hundreds. To wrap up, we have presented a method to mix yarns and triangles in closed simulation. Yarn level detail is preserved in selected regions, while memory consumption and simulation time are reduced. In our examples, the enriched region is fixed due to the cost of recomputing the kinematic filter and the preconditioner. Finding ways of dynamic adaptivity with runtime enrichment is a major direction of research for future work. Finally, triangle energies should match as closely as possible the yarn energies to produce smooth transitions. An upcoming paper has looked at this problem, and it could be an interesting complement to our work. We thank the funding agencies and all those who helped in this project.
Thank you for a very nice presentation and a very inspiring talk. There are some questions for the presenter. And one is that, are the errors influenced by the yarn defined automatically?
Can you repeat this?
Sorry, Jan, but I could not really hear you. Could you perhaps repeat?
Can you repeat the question, please? I didn't hear it.
Okay, thank you. Are the variants influenced by the yarn defined automatically?
They are defined using a texture, so we just paint a texture with red to define where we want to place yarns, and the rest of the model is with triangles. But you can define the region as you want. So any model could be just, you can just put spheres and select all the nodes inside the spheres.
Okay, thank you. Is the combined mass metric sparse?
Sorry, is the combined mass matrix fast?
Yes, that's the question.
The mass is defined. We don't really compute the mass as a matrix. We just do a matrix-free implementation. But it's fast. We just multiply by the variance in the matrix, and then we multiply by the original mass. So it's fast.
Okay, thank you. There's another interesting question about how you handle changes over time where areas that need yarns change.
We don't do that yet because we need to recompute the filter and the preconditioner, and that is very costly. So we don't do that yet.
Thank you very much. And I don't think we have more time for any more questions. I would like to thank all presenters of the session and all the audience for asking interesting questions to us. Thank you for today.